Welcome back. I hope you feel refreshed and ready to move on to 3D printing. Before we do that, I should point out that because the image produced by an inkjet printer is usually a single layer, we call this type of printing two-dimensional. I gave you a few examples before the break where an inkjet printer was used to make multiple passes over a substrate, and in that way it can be used to build up a three-dimensional object. Obviously, we need many layers because a layer of ink is very thin. For the rest of the lecture, we are going to focus on 3D printing, which, as the name suggests, considers printers that do indeed make multiple passes over a substrate, building up an object layer by layer. A 3D printer can use ink, but usually other materials are printed that allow objects to be built faster. 3D printing is often referred to as additive manufacturing, and while I don't think this term is quite as catchy, it does help in understanding how the process of 3D printing works. Think first about conventional manufacturing. Since humans invented tools many thousands of years ago, we have made things by starting with a block of material, like wood or metal, and removing material to fashion our object. In this sense, we can think of conventional manufacturing as subtractive. We start with a block of something solid and we remove material from it to make our object. 3D printing turns this paradigm on its head. Starting with nothing, we add material layer by layer to create our final object, and this is why the term additive manufacturing is used. The reason there are so many types of 3D printer is because each type builds objects out of a different material and or uses different processes to set the material solid, as we shall see in a moment. Before we look at specific 3D printing technology, you may ask me, how does a 3D printer know what to print? And that is a good question. Like any printer, a set of instructions is sent by a computer telling it what to print. To make a three-dimensional object, a 3D printer requires information on what has to be printed to make each layer of an object. To do this, once the object has been designed, it must be sliced into a series of horizontal layers. The easiest way to do this is to design the object in CAD software. There are loads of software options available that you can use to design three-dimensional objects. We tend to use Tinkercad, a link is given below, because it is web-based and free. But with a UCL account, you can also download AutoCAD. If you don't want to design your own objects, then you can download one someone else has designed. The biggest resource is Thingiverse, and again, you will find a link for that below. When you press print, the software automatically slices your object into horizontal layers and sends the information for each to the printer. The printer then deposits material onto a build plate layer by layer to create the final object. 3D printers can make objects out of metal, ceramic, plastic, resin, gel, powder, foods, and probably more. The common feature that links all 3D printers is that they need to be able to dispense the material they are printing and set it solid. Why do 3D printers only print solid objects? I also hear you ask. The answer is that there is no point trying to print a liquid or a gas. Imagine the mess. So the object must be solid, or at least semi-solid if a resin or gel is printed. But how can a printer dispense something that is a solid? The answer is, it doesn't. The really clever part of 3D printing is in how the printer takes a raw material, I call it a feedstock material, think of it like the ink in a desktop printer, which it must be able to dispense and turn into a solid. We will look here at the most common 3D printing types that are useful for printing medicines: powder bed, Fused-Filament, Stereolithographic and Selective Laser Sintering. Powder bed printing which was actually the first type of 3D printer developed, is really a modification of inkjet printing. It combines an inkjet printhead with an apparatus that can dispense powders. A schematic of a powder bed printer is shown on the screen in front of you. Rather than contain an ink, the printhead contains a solution of binder. To make an object, a layer of powder is spread out on the build plate by a roller, and the printhead passes overhead, spraying binder to adhere the powder particles together, forming one layer. The piston on the left rises to dispense more powder, which is spread out by the roller, while the build plate on top of the piston to the right is lowered. This process then repeats multiple times to build up the object. At the end, the object is removed from the build plate, any loose powder is shaken off. One limitation of this type of printer is that it cannot print hollow objects because the loose powder will be trapped inside. But it is the only type of 3D printing that is currently used to make a commercial product. That product, shown on the screen, is called Spritam. It's a product made by a US company, Aprecia, and it was licensed by the FDA in 2015. The tablet really contains just drug powder particles weakly bound together with a binder solution. The advantages of this are very good. There are no excipients, so that reduces cost, limits compatibility issues, the dose of the drug can be high. You can see the product is available in 4 dose strengths, up to 1 gram. 1 gram! That is a huge dose for a tablet. And finally, because the powder particles are only weakly held together, the tablet disperses very quickly when added to water. Aprecia has released a video showing how fast Spritam disperses compared with a conventional meltlet tablet, so let's have a look. Thus, the product is marketed as an oro-dispersible tablet. Often, the cost of manufacturing with 3D printing is very high, compared with conventional powder compaction. So to make a business case, there must be a clear advantage of using the new technology. In this case, Spritam is high dose and oro-dispersing, and this type of formulation would be very difficult to manufacture with powder compaction. The other interesting thing about this product is how Aprecia uses the printers commercially. Rather than have a factory full of printers, each producing tablets, they change the production process so that the printing steps occur on a conveyor belt. But rather than me explain, Aprecia also has a handy video which explains the process, so we can watch that instead.
Let's take a look at the 3D printing process. First, a powdered medicine is spread into a thin layer. Then, a liquid is dropped onto the powder to selectively bind the particles together into a thin, porous layer. This process is repeated a specific number of times to add more layers based on the dosage, building the product from bottom to top. The result is a porous drug product that disintegrates with just a sip of liquid. Learn more at Aprecia.com.
Although it's used commercially, powder bed printers are expensive, so most research labs use cheaper technologies. The most common type of 3D printer, and you may have seen one in our labs or have one at home, is fused-filament printing. In a fused-filament 3D printer, the feedstock material is an extruded polymer, much like a thin piece of string. You can buy them on spools in a range of colours and made of various polymers. The filament is fed into the printhead and melted, turning it into a viscous liquid. This liquid is then extruded through a small nozzle onto a build plate. The build plate is often kept cold, so when the liquid polymer touches it, it turns back to a solid. The nozzle moves across the build plate in an XY raster pattern, building up the first layer of the object. Once the first layer is finished, the build plate moves down and the process repeats for the second layer. In this way, the object is created layer by layer. This was the first type of printer that we bought for our own labs, partly because it was cheap and partly because the fact it uses extruded polymers is a big advantage pharmaceutically. For one thing, the filaments are made with hot melt extrusion, which is a standard technique used in the pharma industry for making drug polymer blends. Thus, hot melt extrusion is ideal for making drug-loaded filaments. Secondly, because it is used in the pharma industry, it is easy to set it up to operate under good manufacturing practice principles, which is required to make products for human use. And finally, and this is something that we focus on in our own research, it is possible to extrude pharmaceutical grade polymers, known as generally regarded as safe, or GRAS. It's really key to print with GRAS polymers if the tablets are to be used in humans, as the commercially available polymer filaments are usually made of ABS, PLA or PVA, and these are not good for human use. ABS is what Lego bricks are made of, for instance. Not good. We use fused filament printing for making pharmaceutical tablets, which we term printlets. Our first paper was published in 2014, and you can see examples of the printlets on the screen in front of you. We realised very quickly that the dose of the printlets could be varied through the printer software. A CAD file really describes only the surface of an object, so you need to tell the printer how thick to print it. Also, if you don't tell the printer to fill the void space inside the object with polymer, you will end up with a hollow object. The amount of polymer that is printed in the void space is called the infill percentage. You can see that as we increase the infill percentage, the printlets become increasingly more dense. This allows us to vary the dose of each tablet without changing the outer dimensions, and is one of the main ways in which 3D printing lends itself to personalised medicines. Each printlet can be fabricated in around a minute. If you're wondering how the filaments actually come together once printed, the SEM images on the screen show you a cross-section of a printlet. You can see the individual strands that were extruded from the printhead and that they have fused together after printing, which is why the tablets are so strong. One benefit of 3D printing that we realised early on is that you can make tablets with geometries that would be really difficult to create with powder compaction. Because the mathematics of the shapes are known, it is possible to calculate their properties, such as surface and volume. We chose the 5 shapes shown on the screen: cube, pyramid, disc, sphere and torus, and fabricated sets of tablets with either constant surface area to volume ratio, or constant mass. All the printlets were drug loaded, so we could conduct dissolution tests to see which geometric factor was most important in controlling the release kinetics. And what did we find? The answer is not what we were expecting. I expected that constant surface area to volume ratio would be the dominant factor. But in reality, there was no correlation, as you can see on the screen. There are a lot of data, but just focus on the purple line, which represents the pyramid. You can see it was the fastest releasing shape when the surface area was constant, but the slowest when the surface area to volume ratio was kept constant. We think the reason we didn't see similar release profiles for all shapes was because once added to water, the printlet swelled and dissolved. So although their geometric features were the same initially, they soon changed during the test. The data also show, again, that you can control the release kinetics from printed tablets very easily by changing shape. Interestingly, or not, this paper is currently the most highly cited of all our 3D printing papers. 445 citations when I last looked, which is, I think, because it contains pretty pictures. I said earlier, it's key to be able to print with GRAS polymers, and the development of printable filaments from GRAS polymers has been a key element of our research. Is it easy? Absolutely not. You can extrude a filament that looks and feels great, is bendy and pliable, but won't print. Or you can have a filament that snaps like spaghetti and it prints fine. Recently, we have been applying machine learning to our data to see if we can get some idea of the likely printability of filaments. We predicted the likely printability of over 900 formulations using this method, and the reference is given on the slide if you want to check that out. The pictures on the screen show 3 filaments printed from varying grades of HPMC, low, medium and high molecular weight, and the corresponding printlets. When we conducted dissolution tests on the HPMC printlets, you can see that the lower the molecular weight grade of the polymer, the faster the release kinetics. Again, this shows a mechanism by which the dissolution behaviour of printed tablets can be controlled. When someone asks us, what dissolution profiles can we make with 3D printing, we show them the following graph, because we can, in fact, make any dissolution profile, from immediate release to sustained release, by varying the type of polymer. Before we stop for further refreshment, I want to look at one other really good application of fused filament printing. Most commercial printers have the capability to print multiple filaments simultaneously, usually 2 or 3. This means you can create tablets with discrete sections, each made from a different filament. On the screen are 2 designs of printlets that are made from 2 filaments. The top design has multiple layers, while the bottom design has a core of one material surrounded by a corona of another. It is possible to fabricate these printlets with different drugs in the different layers, or the same drug in different grades of polymer, or different drugs in different polymer grades. In any case, this is a great way to make polypills. The photograph shows the actual printlets. On the left is the multi-layer design, and in the middle the core shell design. Obviously, with the core shell design you can't see much looking at the outside, so the image on the right shows a cross section, and you can, just about, make out the core and the shell. We tasked an MSc student with drug loading these printlets, and they chose to use caffeine and paracetamol as model drugs. I presume they were thinking of the ideal polypill for a student revising for an exam. Paracetamol to ward off the headache caused by stress, and caffeine to enable staying awake for the 24 hours prior to the exam. We both know you do that. When we print these formulations, we can't know for certain where the drug is actually located within the tablet, so we characterise them with a range of techniques to find out. One of the best techniques is Raman mapping, which is done by my friend Richard at the University of Bradford. Raman spectroscopy is laser-based. A laser beam is focused onto a sample where the light interacts with the molecules present and is then reflected back to a detector. The resulting spectrum is characteristic of the molecules in the material. By moving the laser over the surface of a sample and recording the Raman spectra, it is possible to create a map of the surface, and the maps are shown on the screen. The beauty of the technique is that it is possible to colour code the spectra against reference data. In this case, paracetamol is coloured red and caffeine is coloured green. You can see in the images, which show cross-sections of the printlets by the way, that in the multi-layer formulation the drugs are indeed in separate layers, and in the core shell formulation the caffeine is in the centre while the paracetamol is in the corona. As you might imagine, the dissolution behaviour of these printlets should be different. In the multi-layer formulation, both drugs are exposed equally to dissolution medium, while in the core shell formulation, the paracetamol is exposed first, while the caffeine is shielded in the centre. And indeed, this difference was seen in the dissolution data, where you can see both drugs are released equally from the multi-layer formulation, but sequentially from the core shell formulation. I think I hardly need to tell you that this is yet another way that 3D printing enables the personalisation of medicines. Right, time for another break for refreshment. When we come back, we will finish the lecture by looking at laser-based printers. So if that's okay with you, I'll see you in a bit.